Hi guys, Robin here. Going to look at some binary today. This is part of the A-Level specification, but also was within the GCSE as well. This is appropriate for all of the exam boards, so it doesn't matter if you're doing AQA, OCR. Everything we do here is part of all of those. Okay, so let's move forward. Let's have a look then. So, first of all, we might as well think about what actually binary is. So binary is a representation of numbers, and it works on what we call a base 2. So whereas we use base 10 ordinarily, in other words the fingers of our hands, now we're using 2. The reason for that is because if you think about it, it's easier to show if there's electricity there or there's not. In other words, the state is either on or off. By using that on and off mechanism, we can therefore have a representation. So in other words, if I turn on this first one here, I've now represented 1. If I turn that into a 0, like so, and then turn the next one on, I've now represented 2, and so on and so forth. So you can see how if I do something like this, I'm now representing 10 altogether, because we're simply adding the 8 and the 2 together, which gives us the 10. And so with binary, we generally speaking will use what we call 8-bit. In other words, the 1, 2, 3, 4, 5, 6, 7, 8 boxes that we have here. You can see them, I'm just ticking them now as you go along. You can see we've got 8 of them, and therefore we'd call that 8-bit. In other words, each 1 bit represents the binary number of on or off. We can go up to within 8-bit binary. Our maximum is 255 that we can represent. And obviously what we would then need to do is increase the bit number. So generally speaking, we would double it and therefore would move to a 16-bit scenario. Okay, let's move forward anyway, and let's have a look further. So we've got a few scenarios here. So really, it's one of these things where we want to learn how to actually represent this number. So one of the things that I always think about with this is whether the number that is within the box is bigger or smaller than the number we need. So, for example, if I want to represent, say, 65, I'll ask myself, is 128 bigger or smaller than 65? And because it's bigger, I therefore will give that a 0. 64 is smaller, so therefore I will turn that one on. And then all we're doing then is going to do 65 minus 64, which in this case just equals 1. And therefore I need to turn number 1 on. The rest of them will then be zeros. Okay, if I want to do 37 instead, again, it's smaller than 128 is bigger, so therefore turn that one off. 64 is bigger, and therefore I'll turn that one off. 32 is smaller, so I'll turn that one on. I said 37 into 37 minus 32 will give me 5. Therefore 16 will be off, 8 will be off, 4 will be on. We then have 5 minus 4, which therefore gives us 1, and we're done. What we also need to be able to do is read binary. So if I just put a random one in just to look at it, all we're doing is the opposite now. So I'm reading this, and you can see that I've got 64 is on, so therefore 64, and then I'm going to read across, and I've got 8, and I've got 1. So in other words, 64 plus 8 is 72, plus the extra 1 is 73. Again, I'll just do it one last time just to show us. In this case, I've got 32 plus the 4 plus the 2 plus the 1, and therefore 32 plus 4 is 36, plus another 2, 38, plus the other one, 39. Okay, what I would really encourage you to do is to get good and practice going backwards and forwards between these, because the more confident you are with this, the easier all of binary becomes. It really does. What you'd also notice is that really we're only ever adding the same numbers. So again, you'll kind of get used to sort of adding sort of 32 to 16. So the first time you do that, you sort of, what is that? I've got to think about it. We're actually, once you get used to it just being 48, you kind of do those calculations quicker as well. I'll pick up on that actually. In the exams, you aren't allowed calculators. So again, you don't practice this with a calculator. It's just a big mistake to. Much better to just get used to deal with the numbers. We're not talking about big numbers at the end of the day. Simple calculations really. So it's well within the expectation that you can do that just within your head. Okay, let's move on then. Okay, so once we've established representing our numbers in binary, what we want to be able to do really is to then carry out things like additions and other calculations that you might have. So what's important here though is that we are following these rules here, and you can see them there. So we can see that 0 plus 0 equals 0, 1 plus 0 or 0 plus 1 would equal 1. We have 1 plus 1 equals 0, carry 1, and therefore 1 plus 1 plus 1 would be 1, carry 1. What I mean by a carry is that part of the calculation, the answer effect, is carried on to the next bit. I'll demonstrate what I mean with this scenario set up here. So as you can see, we always start from the right hand side, and you can see that I've got 0 plus 0. So in other words, that will add up to 0. The next one is 1 plus 0, so therefore we'll add up to 1. This is the tricky one. This is the kind of, you have to just get used to this next one. The 1 plus the 1 is the 0 with a carry. So in other words, you can see how it's been passed into the next column, so therefore can be calculated. And what we've now got, though, is this 1 plus 1 plus 1 scenario. So in that case, it will be a 1 with a carry. Now we've got a 1 plus a 1 is therefore our 0 with a carry. Okay, and this is something that I'll do a video about how logic gates work and how calculations are done using circuitry. But as you can see, we've got something happened here. This is what's called an overflow. Because if you notice across the top, we started with 5 bits. In other words, that's what we'd allowed. But what we've required here is a 6th bit. That 6th bit is an additional thing. So this is something that will come back again and again, to be honest, an overflow. But really what we're saying is that it doesn't fit within our pre-allotted number of bits. Okay. And like I say, it comes from the circuitry ultimately, that if you imagine, once you've worked out how to do the circuitry of doing a normal calculation, it's easier to just keep repeating that. But obviously eventually you reach an end where you've got this last one hanging over. It's just something to be aware of. It's not a particularly big deal. It's just something to be aware of, that this could cause an error. In reality, this would cause potentially the calculation to crash, or a program to crash in some way. But like I say, from our point of view, it's not too big a deal, not something we overly need to worry about. Okay, so let's actually do an addition then, so we can sort of see it happening in a sort of real sense. So we ordinarily will deal with 8-bit, and therefore if I just turn on these for sake of argument, so what have I got there? I've got 43, and if I just then add, I'm just going to do something quite random really, do that for sake of argument. What have I got there? 10, 15. Okay, and I'm just going to go through our rules again. So 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1. We've got a 1 and a 1 with a 0, so therefore because of the 1 and a 1, we get a 0, carry 1. Now we've got 3 ones again, so 1 plus 1 plus 1 is 1, carry 1. We've got 1 plus the zeros, which gives us 1. 1 and 0 is 1, and therefore 0 and 0. So now we've got 40, 56, 57, 58, which is the correct answer, isn't it? Okay. Okay, what we want to be able to do is represent numbers in different ways. So we have a different methods of doing this. So what I mean by different ways is by either as a positive number or a negative number. Obviously in ordinary denary numbers, we would just simply put a minus sign, wouldn't we, in front of our number to represent it as being a negative number. In binary, this is the equivalent of doing so, really, in many ways. So if I take just a simple number, so I'll do 11 for sake of argument, so I'll turn 8, 2 and 1 on, and then leave the rest off. If you notice, I've got here at the front, the sort of 8th bit, is we've lost 128. It's disappeared now, and instead has been replaced by a sign, whether it's a positive or a negative. If it's off, like so, is considered to be the positive number. If it's on, like so, that will give us the negative number. So in other words, the top one is a plus of 11 and the bottom one is minus 11. Okay, this is very easy to calculate and very easy to do, but actually causes some problems. And if you think about it, if we wanted to do an addition with this, we couldn't do it, because what we're dealing with here is something that's in a different format to the rest of the numbers, and therefore you can't add that bit together. And just like I mentioned with the overflow being something that's built into the circuitry, if you imagine we had a circuitry that's adding up all of these first 7 numbers to then have to change format on the 8th, just is a problem that just causes issues. So sign of magnitude is very useful for a very quick and easy way of representing two numbers. However, it does have its limitations. So we need a solution to that ultimately, don't we? So a solution to this is what we call 2's complement. Okay, just want to notice up here the minus 128. That's important because what it's doing is it's allowing us to give a negative number. What it's also doing is it's giving us more sort of numbers than we had before. If I just go back a slide, you can see here that what we've actually got is less numbers represented. Whereas with a full 8-bit number, you can go up to 255. We're limited because we've lost that last column. You can see that. So we've got much fewer numbers we can represent. With 2's complement, we now gain a lot more numbers we can show, because we can show all the way up to a plus of 128 and higher, and then all the way down to a negative of 128 plus the additional ones. So it's given us a much wider range of numbers to deal with. And also using this principle, we basically alter whatever is our highest bit number. So in this case, I'm dealing with an 8-bit scenario. We can adjust that. So if I'm dealing with 16-bit, then the negative is just whichever is the most leftmost of those numbers. So it's really quite versatile as well. And also what we gain here is a column that is in the same format as the rest. They're all still numbers. So in other words, what we're doing here is representing a number. So if I want to do a positive number, this will be a 0. And what that means, therefore, is we can recognise this as well, that we can see as soon as you see a number that's in 2's complement that starts with a 0, you know you're dealing with a positive number. And therefore, if I take something like 42, The rest of that shows us, and therefore this will be plus 42. Where 2's complement is less straightforward is I can't just turn this one on and the rest becomes minus 42 because of it being from minus 128. So in other words, every time we turn one of our binary places on, we're adding then to 128. So in other words, if I have the number 2 on, then it goes up to minus 126 for sake of argument. The beauty though with this is there's a very easy and quick way to do it. Okay, so to find the negative contrast, we simply flip the numbers. Okay, so just watch carefully with this. There's a sort of a rule to it. We start on this right hand side and we move inwards in the direction of the arrow. Okay, we ignore any zeros. Doesn't matter how many there are, but we ignore them and we keep them as they are. We're looking for the first one there. We keep that first one, and then all of the rest we flip. So in other words, wherever there's a 0, I now put a 1. Whenever there's a 1, we put a 0, and so forth. This now will add up to minus 42. And it's one of these things with this that by remembering the rules, it gives you confidence. It's not necessarily the easiest thing to do, add up kind of from a negative back up to 0, because we're not really used to that. We're sort of used to always dealing in the positives. So again, it's something that kind of takes a little bit of time to get used to. But like I said, it's something that we can trust therefore and know is going to work in our favour, basically for us. Okay, so what we're also now wanting to deal with 2's complement is the ability to actually carry out subtractions. What we're doing here is we're exploiting the maths, if you like, of the fact that if you add a negative number to a number, what it does is it actually carries out a subtraction. So over here you can see if I do 4 plus minus 2, that actually gives us 2. It's like a quirk of maths that it does that, isn't it? But if you notice, to end up there with 2 is the same as having taken that away. So we're basically exploiting that ability with 2's complement. So if we take a number, let's go with 7 for sake of argument. I therefore have now represented plus 7. I want to get the negative of that, and I want to do that quickly. So therefore, just like before, I go in my arrow from this right hand side, I keep the first one, and then I flip the rest. I've now represented minus 7. All I now need to do is add these two together, so I'm following exactly the same rules as before. So 1 plus 1 is 0, carry 1. 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 1 plus 1 is 0, carry 1, and so on and so on. But what we've got here is a carry. If you're listening earlier on, you'll know what that is. That's an overflow. This happens frequently actually in when we're doing subtraction, and we just ignore it. Yeah, we can ignore that overflow. It's sort of one of the things that, like I say, you see it a lot and we just ignore it. Sometimes it's a good idea in an exam answer to show that you're ignoring it, show that you saw it and you understood that it was an overflow, because they'll generally be looking for the 8-bit number. And again, if you think about it, 7 minus 7 gives us 0, and you can see that we have therefore 0 is now represented. We got the correct answer. Let's look at subtraction then. So I know we talked about subtraction before using 2's complement and the benefit of just being able to add the negative number to a positive number, which created the same instance of a subtraction. And generally speaking, that's the way I'd recommend you do it. It's probably the easiest way to do it, most reliable way. It means you're only really practicing addition to be able to do that. However, there are circumstances when we might want to use a slightly different method for subtracting, just purely because of ease and scenarios. Because if you imagine the problem with 2's complement is you're constantly potentially flipping a number into its negative alternative and that kind of thing, which obviously is it can get a little bit cumbersome and you can get a little bit lost in all of the translations. You've got room for error, if that makes sense. So if we just go through a scenario here. So if I have my first number, let's take something like this for sake of argument, and I want us to take away this from it. Okay. So in other words, what I've got here is 36, 37, and I've got 15 of another. Okay. So what I'm going to do here is take them away. So in other words, 1 from 1 will give us 0. And then 1 from nothing obviously doesn't go. You can't do it. This is something in sort of ordinary denary numbers we're kind of used to borrowing, aren't we? So we're going to do that. So what I'm going to do is I'm going to take from here and turn that into a 0. And when we borrow, because of binary, we borrow 2. Some people write the number 2. I always personally prefer to do the 2 ones. You'll see why as I do this, just because I find it easier to keep track of. So now what I'm going to do is now take away this one from the number above, so I'll take away that one as well. And you can see by the method I've used, I'm left with that additional 1, and therefore I have 1 left. I try again. I've got 1 now from nothing. I can't do that. I need to borrow it. But I've got a problem because the next one is a 0. So I can't borrow from that. The next one along is also a 0. I can't borrow from that either. So I now need to borrow from the one that's in the sort of the 32 column. Okay, so I'm going to do that. Turn that into a 0. And then I bring 2 across. Because I need to borrow from this column as well, I need to get rid of one of those so I can borrow. Again, here, I still need to borrow 1 across. And I get 2 again coming across. What I'm now going to do is take that away, and I'm left with 1. Can you sort of see, by having done this, it's easy now to see what's going on. So in other words, 1 from 1 is going to leave me 0. 0 from 1 is going to leave me 1. And now I've just got zeros from zeros going across. What I'm left with now is 22, which is the correct answer, isn't it? Our next thing that we want to be able to represent in binary is decimal places. It's using exactly the same principle really as before, where we're just turning on a bit and therefore that number is represented. But what's significant about this is we've got the point where we go sort of into the decimal places. So all that's happening here is in the same way that when we move across, if you notice the numbers go up by a times of 2, so 1, 2, 4, 8. Now all that's happening is that effectively it's been divided by 2. So half, quarter, etc. as you move down. But the same process is happening here. So if I want to do this, I have now represented 5.5. Okay. We call this fixed point because we're not moving it. It just is what it is. You can sort of see the disadvantage of that, I hope, immediately, is that in this case, to have an 8-bit number, we can represent sort of very few numbers actually, when you actually look at that. We therefore would need to add a lot more bits to give us more numbers, and therefore we kind of, like I say, we're losing the flexibility as much as anything. So again, as you'll imagine, there's a solution to that. The solution is a floating point. What I'm going to deal with is what I call a normalised floating point. The reason I'll do that is just because I think it's sensible to start with the number as it should be, and then what we can do is look at the scenarios where it isn't as it should be, and then how you fix that effectively. What I mean by normalised is if we have a binary number like so, we assume that the decimal place is here between the first 0 and then the first 1. Okay. What we then do with this is we then have, and this is called the mantissa, we then have what we call the exponent. The exponent is how much you're moving this decimal place by to create whatever number it is that you need. I'll just deal with the positive exponent for the time being, but what that means is that we move the decimal place to the right if it's a positive number. So we'll keep it simple so that you get the idea. And if we just have a simple exponent of 2, in other words, the decimal place is going to move by 2 places, like so. And therefore, if you imagine the decimal place is down here, we're just going to transpose this down like that. So therefore 1, 1 will go there, and then the 0, 0, 0, 0, and then we add in the additional 0, and you can see that we've just represented 3. Okay, so again, looking at floating point, so I just showed you a first number. Let's have a go at another one. So again, we're going to have this normalised. So with the 0 and the 1 will be in the correct place, and therefore the decimal place is in the correct place. And again, I'll just put a simple binary number in. And again, we'll stick with an exponent, and remember this positive is a positive exponent, and therefore we're just going to move our decimal place to the right. So I'll just do a simple one. I'll get a decimal place number this time, so I'll just move it by 1 in this occasion. So in other words, the decimal place is moving there, and like I said, if we then transpose that position is effectively there, the other 2 on the other side of it, like so. And what you can see here is that we've now got 1 point, and then we're adding these 2 together. So we've got 1.75 has been represented. You can sort of see how the fixed point sort of is being used once you've established where the decimal place is. So all the floating point is actually doing is just moving the decimal place to the point where we need it, so that when we use a fixed point mechanism, it then gives us the answer that we're looking for. Okay, so I've just looked at a couple of scenarios where the binary point was moving to the right, and therefore we had a positive exponent. What we may want to do though is have the decimal place move to the left instead. So in this scenario, we need a negative number to do so, and therefore we'll use 2's complement. We'll use 2's complement on the exponent. If this happens in an exam question, they will say this, that they're what is in 2's complement. It might be the mantissa is, the exponent is, all of it is. It's whatever the question is. So you've got to read the question very carefully to make sure you've fully understood what's going on. If it is in 2's complement, we therefore use the first bit on the left hand side, remember, as negatives, therefore it's become -8. We then have 4, 2 and 1. So if I just do a simple number like -1, for example, if I just take a scenario, so this is normalised, so therefore I've got this decimal place between my 0 and my 1, Again, I'm dealing with a positive, like a mantis that's just in its normal form. It's not in 2's complement in this regard. And I've got a number there, like I said. And I just take it. Let's do that for sake of argument. What's going to happen now is that because it's to the left, it's actually going to go in that direction there. So when that gets transposed down into its correct position, if you like, we've now got a 0 here, a 1, sorry, we're doing a 0 again here on this side. So all of those are zeros, and then the 2 1s are here. So in other words, we've got 0.25 plus our 0.125, which gives us our 0.375, and therefore we've represented a much smaller decimal place as a result, and that's what tends to happen when you move it to the left, in all honesty. But yeah, that's what the scenario would look like. Okay, let's look at an unnormalised number then. So this, quite often you see this in exam questions. So we might have a scenario like this, where our mantissa has got all of these zeros in front of it. Again, we're going to assume that the decimal place is here. And again, let's stick with 3.5. So in other words, if 3.5, our decimal place should be there, shouldn't it? To get that, if we want that to be our positioning, don't we? But obviously it's not currently, because it's here where the decimal place currently is. So what will be given initially is the exponent to represent moving it from all the way down there. So 1, 2, 3, 4, 5, 6 places. 1, 2, 3, 4, 5, 6 bounces as it goes along. So in other words, we're going to have an exponent that's represented like so. What we want to do, therefore, is remove these, because it's creating an inconsistency, it's creating a problem. Does that make sense? In other words, the binary should start, the decimal place should start here, and it should just be moving 2 places. In other words, what we've done is we've got rid of 4 movements. Does that make sense? So what we would therefore do is adjust this exponent, and in this case it's now only moving 2 places, so our correct exponent will be this when it's in a normalised format. Okay. Therefore, we now have it in its correct position, and again, if I just transpose that down, our 1.1.1 gives us again our 3.5. Okay, so let's look at normalisation, and we can see here, and we've got a scenario here where I've got all these zeros and a 1. I want to represent 1.75. In other words, the decimal place needs to be in that position there. However, because it's unnormalised, the decimal place is currently here, and therefore it needs to move across. So we therefore would have 1, 2, 3, 4, 5 as our exponent. What we need to do to normalise this is to get rid of all of these zeros, because for it to be normalised, if you remember, it should be here in that position there. So when we redraw that out, we would therefore have 0, 1, 1, 1, 0, 0, 0, and therefore the decimal place is now in its correct position. And again, to still create that 1.75, we're actually only moving it 1 position in this place. So now our correct exponent is so. What we then are able to do is put this into our table, and therefore we get 1.75, as you can see, represented. What we're able to do as well is to use 2's complement on this. So I'm just going to show you that now. Right then, so I just want to look at if we were dealing with a negative mantissa, To do so, we would therefore be using 2's complement, and it has a different look to it, this, so we just need to kind of get familiar with it and recognise what's happening. So what we'll have here is it'll start with a 1 and then it'll be followed by a 0, and our decimal place is therefore between that. So it looks odd because it's the opposite, isn't it? But then when you think about it, that makes sense, doesn't it? Because it should be a flip of a positive number if we're dealing now with a negative number. If we then have, for example, this, of which we're wanting the actual decimal place to be in that position, we're therefore going to move 2 places to get there, 1 and 2, and therefore we'll have our exponent as 2 because we're moving 2 to the right in this case. What that would mean is when we transpose it down into here, we would then have, it would look like this. Which would be minus 2.5. Can double check that, if you don't believe me, by doing the flipping. We can flip this now. So again, remember we're moving that direction. So all of these stay the same, 0s to the first 1. Then we flip the rest. So like so, and you can quickly see it is 2.5, isn't it? In the positive sense of it. Okay, so that's what we're dealing with. But what we would get in an unnormalised scenario like this would be loads of 1s, like so. It could look like that, for example. So what we would be assuming is that the decimal place starts here, but what it needs to do is actually get to here. So therefore we'd be going 1, 2, 3, 4, 5, 6, which we therefore would have an exponent of that. But if you remember, we want to normalise this. So whereas before we were removing 0s, now we're just removing the 1s. And remember, the rule is that it should go between the first 1 and the 0. So in other words, it needs to go here. So we're getting rid of all of these in front of it. So our true movement is actually from here to there, which is 1 and 2, and therefore we change that up there, change that one. It's now got the correct exponent for that. We've now normalised it. Okay, moving on to binary manipulation, bitwise manipulation, and therefore what we call bitwise shifting. All we're doing here is we're taking advantage of the layout to therefore create multiplication and division. So if you think about this logically, if we have, let's stick with a simple number such as 10. If we move it in that direction, so in other words, I take this one here and move it across to here, you can see that I've doubled it. It's been times by 2, so now we've got 20. Again, if I take that even further, so I put it here, times it by 4, and now it's become 40. You can see how that's increased. And again, so on and so forth. Equally, if you kind of look at that the other way, you can also see how we're dividing, aren't we? So if we go the other way now, so if I go in this direction, in other words, I take it back to this previous number, so I'm going from 40 down to 20, I've divided by 2. Okay, so in other words, timesing by 2 by going that way, dividing by 2 going the other way. And obviously that makes it very easy for us to do. With the multiplication, yes, we're limited to still using sort of multiplication by 2, 4, 8, etc. But what we can do is, because with multiplication 10 plus 10 plus 10 equals 30 is the same as 3 times 10, it's the same thing. In other words, if we have our original 10 and we have our 20 position, we can add that together. So if I just quickly do that, so I've got 0, 1, 0, 1, 0, 1, 0, 1, 0, 0. I'm going to add that together using the same rules as before. So 0, 1, 1, 1, 1. Now what we've got is 1, 2, 4, 8, 16. I've got 20, 30 represented. Can you see that? So we've actually just done 10 plus 20, which gave us that 30. Does that make sense? Apologies, I've written over the writing. You can see that works very easily, and you can do that there. You can multiply therefore by any number in a very easy way, as you can imagine from this. However, division doesn't work like that, I'm afraid. You can't just move it along and add them together. It doesn't work that way. We need a different technique to do that. So I'll talk about that technique now. Okay then, so let's have a look at division. So let's have a look at a number such as this. So what have we got there? 1 plus 4 plus 16, so 21 being represented. And let's do it by 3. So in other words, with 3 and 21, 7, isn't it? That we should expect to come out. So how do we do this then? So what we do is we look at our 2 ones and we ask ourselves, does it go into 1? The answer is no, it doesn't, does it? Therefore, we're going to bring that 1 down and we're going to bring the 0 to join it. So it's now here. We ask ourselves, does the 2 ones go into our 1, 0? No, it doesn't. And therefore, we then bring our next one down to join it. We ask ourselves, does 11 go into 101? Yes, it does. With ordinary division like this, you would multiply by the number. We're always dealing with 1, so actually it's really easy for us here. So we're always left with the same additional number. But what we do need to do in the same way as when you do division by this method, in an ordinary denary sense, is to subtract. So therefore, we're now going to do a subtraction. And this is why I just showed you that the subtraction method, because it's just quick and easy to do now. So 1 from 1 is 0. 1 from 0 I can't do, so therefore I'm going to borrow and therefore remove. I'm left with 1 and 0. I've now got 1 and 0, so I bring this one down to join it. I'll let the 1 1 into the 100 goes in 1. And again, going to do the same thing. So going to remove the 1 1 from it, so I'm going to subtract it again. So 1 from 0 I can't do. I need to borrow, so I need to borrow from here. I bring my 2 across. I'm going to take one of them and bring 2 here. So I take my 1 from there and I'm left with 1. I take my 1 from 1, I've got nothing left, 0 and 0. And then eventually I'm left with the 1 here, so I now bring that last one down, like so. I'm left with 1 1. Well, that's the same, therefore it's going to go into 1, and I've finished because I've got nothing left down here. If I was to carry out that sort of subtraction, I'd be left with 0, wouldn't I, anyway, from 1. And therefore we're left with 7, aren't we? Okay, last thing I just want to talk about is using hexadecimal. So the thing to note with hexadecimal is here, at this line here, that all the numbers in denary are the same as they are in hexadecimal. So 0 to 9 is exactly the same. The binaries are easy to work out because, again, they're just 9. So we're using the 4 bits, and you can see that we've got 8 plus 0, 0 plus 1 gives us 9. So again, dead easy to work out. The tricky bit, if you like, is remembering that 10 is actually A. So 10 is represented by A, and therefore we go up in the alphabet from then on, all the way up to F, which is 15. Okay, so if we then take our scenario, let's use 35 for sake of argument, we therefore need 32 on, 2 and 1, like so. So we've turned the denary of 35 into the binary, and then we want to get the hexadecimal. So if you remember, we were just dealing with 4-bit binary before in the hexadecimal table, so in this table here. So all we're going to do is we effectively divide down the middle. Okay, so you can see that we've got 0, 0, 1, 0 on this side, and then 0, 0, 1, 1 on this side. So what we can do with that then is you can see that we've got, in this case, we've got 2, and in this case, we've got 3. So the hex of 35 is 23. Nice easy number. I'll do that again with a different number. So let's do this now with 45, for sake of argument. So again, that's going to be on, what do I need? I need a 8 and a 4 and a 1. Give me 45. So again, I'm just going to transpose this down here to this other table, where, if you remember, we chopped it in half down the middle. So on this side, I've got 2 represented, and then on this side, I've got 8 plus 4 is 12, 13. So what we don't write is 13. Instead, if you remember, because 10 equals A, therefore 11 will be B, 12 will be C, and therefore 13 will be D. So in other words, the denary is 45, the binary is this number, and then the hexadecimal will be 2D. Hi guys, thanks for watching. Really appreciate it. Hope you've found that useful and you've hopefully learnt something. Please do like and subscribe to the channel, and hopefully I'll see you again. Thanks a lot.